Hello, everyone. I hope you can hear me fine. I think we can start. Is everyone here? Just wave a hello on the chat or unmute yourself and just let us know that you're here and ready to start. Okay, perfect. Okay, awesome. So just a quick presentation. I'm Hajar Benouzian. I'm an instructor with the Code Labs Academy, and I'm doing my PhD on AutoML and neural architecture search. I'm also working on natural language processing. And this tutorial or this workshop, we will like try to solve the question answering tasks using some machine learning, of course, and deep learning. Okay, so I think people are still coming, so maybe I'm just gonna wait till 02 or 03 just to talk about the full workshop agenda, and then we can start. Okay, one quick remarks before we start. Please stop me at any time if you don't understand anything. Just unmute yourself and ask your question, or pop a question on the chat. I will look at it while I will present. And yeah, and don't hesitate to ask any question you'd like, even if it's like basic machine learning, because we are going through NLP and transformers, which are a little advanced, but don't hesitate to ask any question you have just in order to understand everything. And of course, we're going to have both codes and presentations. So I'm going to start by presenting the overall what's machine learning, what's NLP, and how can we use machine learning in NLP, and then some of the models, etc. But also we will have to code. So if you want to code with me, just let me know. Otherwise, I have a notebook that is ready, and that we can go through and analyze each line. Out of context, but can I connect with you on LinkedIn? Yeah, of course. You can look for my name and first name and last name, of course. And of course, you also can connect with me via the email. I'm gonna send it here. collabsacademy.com. So if you have any further question after the workshop, you can of course contact me on this email and I'll respond. Yes, the recording will be available later on our YouTube channel. All right. If you don't have any further question, we can start. So in this workshop, I divided it into 3 different parts. So the first part, I'm going to talk about NLP in general and how do we deal with text in a computer. So we know that images are a bunch of pixels. So we know that, okay, intuitively, we know that pixels are numbers. So we can deal with them just like we deal with numbers. But how do we deal with text? So we're going to see this, and we're going to try to create some embeddings and play with embeddings and what are the meaning of embeddings. So basically, as a first glimpse here, embeddings is how we convert words into or text into numbers or vectors of numbers. And then, which is really important because all deep learning deals with is numbers and vectors of numbers. So we need to know how to convert all these texts and words into numbers. And then in the second part, we will discuss what's language modeling, which is the first task that we're going to solve with deep learning models. And then, of course, we're going to discuss some architectures. So in deep learning, we have these neural networks, and then the connection between each node in the neural network and the operation within the node creates different architectures. So we have transformers, we have recurrent neural network, we have the well-known convolutional neural network for computer vision, but we also have different architectures. So we're going to discuss which are the architectures that are the most promising in NLP and natural language processing, and the task that we are going to solve, which is question answering. And we're going to discuss one of the transformer model, which is BERT, which has like state-of-the-art results, but we're going to discuss it deeper because we're going to use it in the code, etc. And then the third part, we're going to go through question answering and explain the task and solve it using, of course, BERT architecture to solve the question answer. And we're going to also discuss what kind of data sets are we going to use, what are the different types of question answering, etc. Okay, and then you'll see here in the slide a QR code. So what I wanted to do is I wanted to create a small poll at the beginning just to assess like your knowledge of machine learning. Feel free to answer the questions. It's really up to you. I just sent the link on the chat. I'm going to send it again because some people just came in. But basically, what you can do is you go over the Slido and you just answer the question. So the first question I put here is machine learning is a subset of. Is it deep learning? Is it artificial intelligence? Is it data learning, etc.? So I'm just gonna assess what you know and what you already know, because it's really gonna help me like go into the details or not of some part of the talk. So please go into this link and try to answer machine learning is a subset of what? Is it a subset of data learning, deep learning, artificial intelligence, or none of the above? Okay, 14 people answered, 15, perfect. Okay, just gonna send the link again. If someone doesn't have it on the chat, you can check the link on the chat. You can also use the QR code on the slide to access the poll. In the poll, we are asking machine learning is a subset of what? Is it a subset of data learning, deep learning, artificial intelligence, or none of the above? So I think I'm gonna show the answer here. We have already 17 people answered. Okay, that's great. Out of 28, come on, people, you can answer it. Okay, 19 people out of 28, that's good. Okay, I think I'm gonna stop here. We have 20 people answered. I'm gonna show the correct answer here. And the correct answer was artificial intelligence. So machine learning is a subset of artificial intelligence. I just launched another question, but I will, of course, explain this. So we know that machine learning deals with data and deals with of course, deals with experience. From the experience, we learn something, and then we apply it in the real world or in new instances. And basically, this is what machine learning algorithms does: learns from the experience and then apply it in a real life scenario or with real life instances. And artificial intelligence is the science, or englobe all the algorithms that uses that makes the machine decide, basically. So whether we have like an if and else, an expert system that makes the machine decide whether to turn off the light or not, this is artificial intelligence. But also machine learning is a subset of artificial intelligence. And then we also have this deep learning. So deep learning are machine learning algorithms. So they also learn from experience. They also learn from data, but they use this special neural network algorithm model. So this is what deep learning is, and this is what machine learning and artificial intelligence. So to answer the question, machine learning is a subset of artificial intelligence, which most of you got correct. Perfect. Okay. And then we have another question that pops up. If you can go in and answer it, I'm going to send the link again. So we are now 32. Let's hope for 20 answers in the question for the question. So the question is, pandas is used to deal with tabular data. Is it correct or not? Is it true or false? So we all know that pandas is a Python package, but why do we use it a lot in data science? Is it to deal with tabular data? Is it to deal with images? Is it used to deal with text? Is it used to deal with all of them? But if it's all of them, then it is used to deal with tabular data. So is it true or false? All right. So we have 20 answers. That's really cool. And we have 90% for true, which is the correct answer. Perfect. So pandas is used to deal with tabular data. We have this great, we can display our table really fancily in our notebook, and we can see all the columns, we can see all the features, what we want to predict, etc. So it's really cool to deal with to deal with tabular data in like SQL, just like SQL, because we can have we can query different things in our tables, we can get different things from it, we can select different rows, etc. So it's really cool to deal with tabular data using pandas. All right, last question, and then we start talking about NLP. Okay, if you can go inside again one last time. And the question is, in linear regression, we try to minimize, maximize, nullify, or change the least square errors of the model to identify the line of best fit. So is it to minimize, is it to maximize, nullify, or change? Just give us your intuition, your knowledge about this. So in a linear regression, we want to find a line that fits the data. We call it the line of best fit because it's best fits the, basically, yeah, it is the line that best fits the data. So is this line, when we try to learn this line, when we try to learn the parameters of this line, do we minimize the least square error, or maximize it, or nullify it, or change it? Okay, we are at 16 answers. Can we go up a little bit to 20? Come on. 17, perfect. All right, 19. Just waiting for this 20 in order to start. All right, perfect. I'm going to show the correct answer now, and the correct answer is to minimize. So usually the loss function, we want to minimize it, and we use for that some gradient descent or something like this, or some optimizer like this, just to get to the minimum, to get to the parameters that gives us the minimum of the least square error. And if you don't know this least square error, it's basically the distance between all the points in the true values and the predicted values. So it's basically the distance between all of these. All right. So I think now we can start with our machine learning in NLP. And one thing we can start off is what's natural language processing. So basically, we know what is a natural language. A natural language is our language that we talk. So we have English, French, Arabic, German. We have different languages, and we want to process them. We want to have a computer that understands it and maybe do something with it. So we have different tasks here that I just cited a few here in this slide, but we have a lot of different tasks. We have sentiment analysis, for example. In social media, we can have we can use it to know if this post is I don't know, maybe if it's hateful, or if it promotes love and compassion, if it's something that is hateful and we want to reduce it, and we don't want to show it, we don't want to recommend it. Or maybe we have text classification. We want to know if this post talks about mental illness, or if this post talks about technology and security, or anything like this. And then we have summarization. This is a really cool task where we have a really long text and we want to summarize it. We want to learn only, if it's a student, he wants to learn only the the most important information just before the exam. And we also know we have, of course, translation, where we translate from one natural language to the other. We have auto-completion. So auto-completion basically is what we found in our phone keyboards. We start by writing the first letters of the words, and it suggests different things. We have intent detection, where we have two sentences and we want to know if one is the cause of the other or one is the consequence of the other. So basically, we were doing this when we were young in school, and we thought, what if a computer can do it, and it will understand like the meaning of each sentence and to get what a consequence and what a cause. So basically, this is what intent detection is. And of course, we have, I just missed the explanation of two tasks here, and it's on purpose. So I didn't explain what language modeling is. And basically, as a first explanation, language modeling is to predict the next word in a sentence. So if I have a sentence, okay, natural language processing is what we are, and I stop here. Maybe the machine, the model will predict the next word. So it's going to say learning, what we are dealing with, or something like this. And of course, we have question answering, which is the task that we are trying to solve here today. And what is question answering? We're going to see it, of course, in a slide, but basically in one sentence, we have a question. We want the machine to answer it based on all the data that we gave the machine. And of course, there are plenty of different tasks that you can think of here. If you want, just send us some examples on the chat and we're going to discuss it. Can you let me know if you're hearing me? Because Eugène Bordelon, I am not getting any audio. Okay, you're getting it. Okay, perfect. Okay, perfect. Thanks. Perfect. Okay, and then are you presenting your desk? I am presenting the slides. Can you just confirm that you're seeing the slides and you're on slide 3? Okay. Most of you are seeing the slide. Carolina, can you try to go to disconnect and then connect again? Maybe it will work. Okay, can see the diagram. Perfect. Thank you all for answering. And then we have some question. Language modeling, is it different from predictive analysis? Okay, predictive analysis is mostly used from data analysts when they want to have like a direct answer. But here in language modeling, we want to create a model that really understands the language and that can predict a next word in any context. And then what's the difference, by the way, between auto-completing and language modeling? Okay, that's a great question. If you see in your keyboard, in the phone keyboard, if you start just one letter, it will try to auto-complete that letter, auto-complete the word. And that's what's happening in auto-completing. But in language modeling, we don't get this instant from one letter, we try to fill the blank, but we try to fill the sentence with other words. It can be seen as part of auto-completion, but language modeling is much deeper than that, because auto-completion for now in our phones, for example, doesn't really use deep learning. And it only uses deep learning as a keyword spotting, just to check which word is used in which words you typed, and then based on that, it will suggest other things based on what the users are doing. But then in language modeling, we are trying to have a model. We are trying to have a machine that will automatically create its own text, for example, generate its own text and generate its own script. All right. Let me know if you have any other questions, and I'm going to continue here.
Hello.
I just heard someone. Yeah, hello.
Huh. Yes. So I just want to know, means is language modeling is more of a probabilistic method more, is it?
It is based on a probabilistic method, but we are going to learn it via a mod via deep learning. So it's true that in machine learning, of course, if we have a sentence, we have a probability to have that next word. For example, if I have a noun, I can calculate the probability of having a verb after that noun or an adjective after that noun. And then based on that probability, I can predict. Of course, these probabilities will help us, which is used in Glove, for example. Glove use occurrence and a probabilistic model to predict all these. But then we are going to talk about BERT, and BERT uses deep learning to solve this problem. Is that answer your question?
Yes, yes. Thank you.
Perfect. Okay, and then okay, just a glimpse of what's machine learning. So machine learning is an approach to achieve artificial intelligence. As we said, it's a subset of artificial intelligence through, of course, experience. We are learning from experience to find some patterns in a set of data. So, for example, before machine learning, this is an example to catch a spam. So what we were saying, if the email contains the word free, maybe in capital like this, then it is categorized as a spam. Else we look for more keywords, I don't know, maybe 100% or all the words that are in capital 70 with font size 70 and in red or something like this, something really flashy and fancy, we consider it as a spam, or other keywords, of course. But using machine learning, what we are going to do, we are going to write a program that learns these patterns from itself. So we are not going to specifically say, okay, this is the condition to have a spam. We are going to give it a bunch of different emails, and we are going to say, okay, these emails are spams, these emails are not spams, and it's up to you, it's up to the machine to find what is the pattern or what is the condition that makes these a spam and these not a spam. So basically, the algorithm will look like something like this. So we will have try to classify the emails that we gave you, calculate the error because we know which email is a spam and which email is not, and then we adjust based on that, and we repeat that 100 of times or a number of epochs. This is what we call epochs here. So we repeat that a number of times until we learn, until our model, we are satisfied with the result of our model, or until we minimize this calculated error. So basically, this is the difference between what we are going to do with machine learning and what is explicitly done before machine learning using explicit conditions. And then what I said is we are going to start with how to deal with text. We know that text is not, we don't have like numbers in text. Of course, we treat text as a language. So how can we transform these texts into vectors of numbers so that we can deal with them using in our codes? So one thing we have is, let's say, one easy or intuitive way to do it. We have the vocabulary. We know that, okay, I have a vocabulary, I have a dictionary of different words, and then I will assign an index to each word. So let's say have has an index of 1, a an index of 2, word 1 is 0, and I is 345, dog is 1760, and then we give like different indexes to each word in our dictionary. If we have 100,000 of different words, we would have 100,000 indexes. And then if I have a sentence like this, I have a dog, I can create this vector just by replacing each word by its index. So let's say I becomes 345, have becomes 1, etc. So this way, I can transform each sentence into a vector of numbers. So one question I have here is, can you intuitively think of a reason why we can't use directly this vector? And this vector is not good. Can you think intuitively why this vector is not good? of course, here each sentence will have a vector of numbers. So our goal is done. So we would have like numbers in each vector, numbers for each word. So we would have a vector for the sentence. So the goal is reached. But exactly, so Fabian just said the correct answer. There is no semantic here. A sparse matrix, why do you think it's sparse here? So we are replacing each word with its index. So we don't get really sparse matrices, but we would get sparse matrices if we were to use one-hot encoding. So one-hot encoding is another way to do it, and in this case we would get like a sparse matrix. But here we wouldn't have a sparse matrix, but exactly as Fabian said, we would have no semantic. So that means if, for example, if I have, let's have two words that have the same meaning. Okay, if I have a verb and it's past tense, these words have like some semantic between them, so they are similar. They have the same meaning, except one is in the past and one is the infinitive, or one is in the present, for example. And these words, I want my model to know that this one is the past form of this one, and when to use the past form and when to not use that past form. So if I want to do this, and if I classify my vocabulary like this, I may have like, okay, the verb will be as indexed 1, and the other one, the past form will be indexed 2, or will be indexed 1000, or any number. So that means that the verb and its past tense won't have any meaning between them. And we need to find a way, of course, to have meanings, just to keep these semantics together and to know what's happening there. Okay, and this is where word embedding comes into the play. So what we want to do, we want to add some meanings to each word. We want to have some vectors that represent each word and that has some meanings inside. So what we're going to do is that we're going to create, so of course, we're going to transform it to this kind of vocabulary vector. We're going to say, okay, I is the 345 word in my vocabulary. Have is the first word in my vocabulary, but I'm not going to present them like this to the model. I'm going to learn some embeddings or some vector to represent each word. So I'm going to have a vector for each word, and this vector will hold some information that relates to the semantic, relates to the word itself, etc. Okay, so ultimately, what we want to get, and word2vec here is one of the most promising word embeddings used. So I'm going to start by the conclusion and then get to the how to create word2vec. So basically, ultimately, what we want to get is we want to have the same relation, for example, the same distance between the two vectors of man and woman and king and queen, because we know that the relation is the same. So we want to have the same distance. We also want to have the same distance between walking and walked, swimming and swam, because one is the past, one is the present. And then we want to have the same distance between each country and its capital. So we want the word embedding to hold some information about the semantic. And one way to do that is to create some machine learning model or deep learning model that learns the word embedding, and then use this word embedding in our model that learns to do language modeling or question answering. So we have a previous step, a previous deep learning model that will learn the word embeddings. And once we have the word embedding for all our vocabulary, so we would have a vector for all these words in our vocabulary, we can use these to give our language model or our question answering model to train these models. Now, in this situation, what we're going to do is that we're going to learn, we have two kind of types of word2vec. So we can learn the embeddings from a continuous bag of words or from a skipgram. I'm going to start by explaining the continuous bag of words, but they are pretty similar just in terms of input and output. They differ in terms of input and output. So basically, in continuous bag of words, what we are trying to do, we are trying to do a language modeling. So we are trying to predict the next word. So we give it, I have a, and then a pad. And this pad will reflect what we want to learn. And the output will be dog, because we want to complete this sentence. So to complete this sentence, I will say, I have a dog. And the embedding of dog, what would be the vector that represent the embedding of dog would be the weight vector of the path from the padding, I have a pad. So we would, of course, in a linear regression, we would learn some parameters, and these learned parameters will represent the word dog. And similarly, in skipgram, as I said, the difference is only in the input and output of the models. So here we would give it what we want to get. We would give it the name, the word that we want to search for the embedding for. So we would give it dog. And then the output would be the sentence. So we reversed the input and the output. So we would give it dog. We would also give it like a length, a specific length. So we want all our vectors, regardless of the length of the word, to all be 4, for example. And then we would give it like 4 times dog. And then using the linear regression, we would learn something, and then we would get here. I'm sorry, I'm saying linear regression, but it's not linear regression. It's actually a linear layer. Here, it's different nodes that are fully connected. And then we would have to I have a pad. And using this, doing this for all the vocabulary in our word and for all the sentences that we have in our data set, then we would get to the parameter. Then we would learn the parameters here, and we would give these parameters to dog. And basically, dog would get this vector. Okay, I'm gonna stop here and ask for some questions. We can go to the
What is the cost function for word to vec?
Yeah, so the cost function will be like a direct classification. It's like a classification, because we know what we want to get, and it will be like a supervised way of learning.
So means it is, I'm not able to understand the nature of the data set. If you are saying supervised, so what is the label and what is the data set? What is the data and what is the target?
Yeah, so we have the data. The data set will contain different sentences, right? The dataset will contain all the sentences that we want. If we have like all the different texts, not only the sentences, but we are going to tokenize them. So we are going to get different sentences. So the dataset will contain different sentences, and we will mask different words in each sentence. And each time we mask a word, we try to predict that word. So we have the label, we have the masked word, and we are trying to fill in that masked word in the sentence. So here I put like the pad in I have a dog, but the pad could be put like, we could put the pad in have, and we would have I pad dog. And we would try to find the word embedded for have. Is it okay?
You mean to say, so suppose the sentence is I have a dog, and so the data set will have a data point where I have pad dog. Sorry, I pad a dog, and your
Exactly.
target will be have.
Exactly.
Okay, so this is how you form the word embeddings.
Yeah, exactly.
Or is it exactly how word to vec works?
Yeah, this is exactly how word2vec works. So word2vec is the skipgram version.
Okay. So how do you decide? Means you randomly pad some words. So like I have a sentence which is of 5 letters, 5 words. So I can have 5 data points from that sentence. So is there any some heuristic to decide which words, which first word, second word, which word to pad and all?
Yeah, so for example, in BERT, we mask 15% of the word. So they have like some probability to say, okay, I'm going to mask 15%, 10% of each sentence to create some more, to generate some more data points.
Okay. Thank you.
Okay, no problem.
So means that means, just to summarize, that means that this entire training, the goal of the training is to learn predicting some word, but because of this training, word embeddings also get learned.
Exactly. This is exactly what's happening. So we have this goal. The training goal is to predict the word, but then we get the word embedding from inside the model.
Okay, good.
Okay.
Yes.
Okay, I'm just gonna stop presenting because I cannot switch to the visual code. So maybe I'm gonna present my entire screen like this. All right. Can you see my entire screen? Hello? Oh, yeah. Okay, perfect. Okay, perfect. Okay, so I'm just gonna use the word2vec models. So what we have in the literature and what you can find on GitHub, you can also find them in the literature. But basically, I'm gonna send you the link on GitHub to find the models. So we are not going to train the skipgram word2vec model. We are just going to use it and try to get some embeddings from it. So basically what you get is you can try to load your model and load your vocabulary. So these models were trained on Wikitext. Wikitext is a data set that contains different Wikipedia articles. And it's really rich because it contains different words, different context, etc. So we can learn, we can really learn from each word like a really good embedding. Don't forget that we also have some words that have similar, different meanings, but similar writing, so or spelling. So we would get like the same embedding, but we would try to increase the values of each vector, or the word embedding will hold different different forms or different semantics in it. Okay, so here I'm gonna load my models. So like this, my models in on the folder, on the weights folder. So I'm just gonna load my model and my vocabulary. The vocabulary, of course, is just a list of all the different words that we have in our data set. And then we're gonna extract the embeddings of the first model layer, because this is where we hold the embedding. And then we are going to normalize them. And basically, we would have 499 embedding with 300, and the dimension of each embedding is 300. So I think you can find in the literature different word embedding with different dimensions if it's required by a model, but 300 is fine for us. And then we can visualize using TSNE. So TSNE basically is like a dimensionality reduction technique. Just because we cannot see 300 dimensions, of course, we will just reduce it to 2 dimensions just to plot all the different words that we have in this data set. So I guess we would get this. Okay. And we would get different, so all the different words are here marked: society, valued, awarded, charge, etc. And all the numeric letters, I printed them in green. So if you see a numeric value like 1957, which is a date, or maybe we can see 0 here, we can see 52, 33, etc. So we can see different. I'm just going to pop to the chat and see if there is any question. Okay, perfect. Yeah, we can see different numeric values that are in green, and all the different words are in black here. But we have like a variety of different words and different and different words in our data set. So what we are going to do is that we have this function which gets the top similar word. So we are gonna verify what we did what we claimed previously. We said that, okay, we wanna have the same distance, or we want to get similar embeddings for all the countries, similar embeddings for all the different capitals, etc. So maybe what we are gonna do is that we have this function get top similar, and basically what we are doing here is we are computing the distance between the different embeddings, and the top ones we are just going to print the words corresponding to this top similar word. We are also going to print the similarity. So for example, if I give, okay, for words and similarity in get top similar, this function will return a dictionary, and the dictionary will the keys of the dictionary will be the words, and of course it will contain the similarity, so by how much we are similar. Okay, no questions. Perfect. So I'm gonna just give it like the word Germany, and I'm gonna try to print all the different similar words. And we have like France, Italy, Netherlands, which are all close neighboring countries to Germany, which is cool that we have this kind of semantic. And then we have Europe here, so that's cool. Do you want to try any other word here to get the similar words in the dictionary? I'm just gonna check the chat. Okay. Okay, mother. Let's go for mother. Oh, this word, oh, maybe it's because of the, yeah, it was because of the M, capital M. Everything is in low letters, so the capital M is removed. Okay, we have father. Weird, we have husband at first, and then father, daughter, wife, brother, parents. Okay, that's cool. Childhood. India. All right. All right. Independence, empire, Croatia, which is a country, but Indian. Of course, all these words depend on what kind of text we gave to the word embedding. I don't know if this model was trained enough on this data set, and if also this data set contains all the articles in Wikipedia. But it's cool to see like what kind of words are similar to the word India in the data set. Okay. Okay, Canan, I really don't know. I'm gonna send my code, but if I'm gonna ask and let you know, okay? But I can send you the code, of course. All right. And then we also have this cool thing that we can do, which is vector equations. So we can have like different embeddings, and we can compute like, okay, we have king, man, and women, and we can compute king minus man plus women, and we can do different embeddings and then get to the top similar word based on this. Okay, and then we get like king, rain, sun, women, daughter. We would of course expect to have queen here when we do king minus man plus women. Again, I didn't train the word to vec, and we would need to train it from scratch, but it would take like a day in a decent GPU. But yeah, of course, in a cluster, it would take much less. But yeah, we would expect it, of course, in a good embedding, we would expect to get here king minus man plus women, we would expect to get queen. It's a great, it's a really great thing. Yeah, it's more like related to the word. Of course, it's not it's not similar, because if we get similar, because we are trying to learn these embeddings from the context. So we would have like, okay, we have mother, and in the same context, we always have father. So this is more like, it's not, I'm talking about similarity because we compute the similarity between the two embeddings. So it's like more a metric than similarity in terms of semantic. So it's not, yeah, maybe it's not similar word, but related word. And more specifically, it's words within the same context. So words that we found in the same sentences and that we found related to each other. It's a good remark. Thanks. All right, let's go back to these slides, and we can go back to part 2. So that was how we created the word embeddings and what we played a little bit with the word embeddings, just so we know that we can do some vector encoding. We get our words, and then we can play with them a little bit, just to know. For example, we can do different operations on them, and this is what we are going to do in deep learning, actually, because we would give all these different embeddings, and then we would get like different multiplications, different activation functions, etc., to get to the output that we want to. So we would transform these and combine them in the sentence, etc. Okay, so now part 2. And in part 2, we're going to discuss what are the different architectures that are used to deal with these texts. So the first one I'm going to start with, and it is a really important type of neural network, which is the recurrent neural network. So before transformers, I know that now we hear a lot about transformers, but before transformers, we were using recurrent neural network for texts or sequence data in general. So sequence data is any data that comes with time. So we have, for example, a video is a sequence data because we have the first frame, second frame, third frame, etc. As a text, of course, is a sequence data because we have steps. We have the first word, second word, third word, etc. And we were using this recurrent neural network. So there are different types of neural networks. The well-known convolutional neural networks are good for computer vision and images. Although now transformers are starting to get really promising results in computer vision as well. But let's not discuss that. Recurrent neural networks are good with sequence data because they have this kind of recurrence in the node. So if I have this sentence, I have a dog. Of course, we would get the embeddings of each word. As I said, it's the word embedding is a preliminary step before going to our language modeling or question answering model. And we are now talking about our language modeling model. So basically, we would get the embedding, and then we would give the embedding to a certain node. And this node would give us the first output, H1. Okay. And then the second node, we would give it the second word, but we would also give it this H1, the result of the first node. And this is more likely, intuitively, this is really easy to justify, because if we want to predict dog, for example, we would have to say, okay, the node would have to get the information from I, have, and to get to dog. Or maybe if we want to predict have, then we would have to get the information from I and etc. But the first recurrent neural network were like, okay, each word in the sentence would get the information from the first, the previous words before it. So if I want to predict A, we would get the information from have, which contains the information from I, etc. Okay, so basically this is a recurrent neural network because each node would have a recurrence, each layer would have like this recurrence in it, because we would have the output of another node inserted in it. Okay. I'm just checking like the chat if there is any question. So please stop me if you have any questions at any time. Okay. And then these were, of course, as I said, if I was to predict have and I would get only I, it would be difficult for me to get to have. But if I have I and the information of a dog, it would be easier to predict have. And this is why we also have bidirectional recurrent neural networks. So we would have the information from here to here and also the information from here to here. So this is also happening, and this was also one of the models that was the most prominent. And then inside this node, we would get like different types of operations. So basically the first ever recurrent neural network, we would only do a hyperbolic tangent here. So only one activation layer, and that's it. That was the first recurrent neural networks, and it worked, yeah, let's say well, but then there was like some more prominent works, of course. And then we have this famous Lstm cell. So the Lstm cell contains different activations, one after the other, and really in in an adequate order, so that we get different gates and different results. So basically,
I think your screen is not updating actually.
oh,
It is still stuck on RNN.
no, I'm just like talking about the LSTM, but I don't want to show it here because we're gonna mostly focus on transformers. So I just wanted to let you know that we worked, so previous to transformers, we worked on the inside of this node, trying to get more operations in it, trying to get more results and more information that goes to the next node. Okay, thank you.
Yes, okay.
All right. And then, yeah, of course, the task that we want to solve at first, I'm going to justify why we want to start with language modeling. And language modeling, as I said, is predict the next word in a sentence. A cool task is Hugging Face. I don't know if you know it or not, but maybe we can go inside and try a bunch of different text. So one thing we can do is, this is using a language model, GPT-2, and we can use, okay, we can say, just give me a sentence, give me a starting sentence, and we can ask the model to fill in the blanks or to predict the next word. Do you have any example you want to test?
Yes, you can try. We are having a great learning experience. You want to predict experience.
We are having a great, and okay, maybe learning and then experience. Okay. So we have like curve in our community, and we have a great opportunity to do that, or experience with the way I work. And the way I work, what? Okay. Curve and learning curve. Oh, okay. And I feel comfortable with the direction, which is, oh, this one is pretty like has like a lot of sense. We are having a great learning curve, and I feel comfortable with the direction. Okay, but we can try a bunch. Okay, let's say experience and then dot. We can also ask it to start the next sentence. If we don't make progress for the year, we're going to be down. It's going to take a lot of hours to get started on this. It feels good to have a great experience and a little bit more experience. What? Experience to enjoy working with the team, to help us develop better games. Okay. And just so you know, this example and this GPT-2 was like, was like deployed a few years ago. So we can really like expect like more from GPT-3, which is an updated version of this model, and expect more from a real locally trained model, because these were trained to be deployed on a server. So maybe they were trained with less number of epochs, etc. So we can expect a lot more from a bigger model and a much more trained model. Yeah, so I'm going to just post the link here. And if you have any sentence you want to test, just feel free to play with the transformers. All right. So basically, this is language modeling. So we predict the next word in a sentence. And then, and then one thing I didn't put a name on is self-supervision. So before I was saying, okay, we can mask this word, and then we try to predict that word. Or we can remove that word and we can try to predict different, so we can create different data points in our data set using one sentence by removing or masking different words. And this, I didn't put a name on it, but basically it's self-supervision. So self-supervision is when a model create its own data set. So based on different sentences, we would give it different sentences, and then it will train and create different version of the data set, try to fill in the labels by itself, etc. So here in BERT, which is the model that we are going to use, we are going to fill, of course, this black box here. It's just a blue box here, but we are going to know what is the content of what kind of operations are applied in this model. But basically, we have I mask and then a dog, and the model will predict I have a dog, which is a masked language modeling, because the original language modeling is only predicting the next word in a sentence. So directly the next word. Of course, here in the example, or in this deployed transformer, you get a complete sentence, because they call the model different times. So they are not calling the model only once. If they call the model only once, we would get only one word, but you call the model different times to get a full sentence just for the point, and then once you get the points, you're fine. And then in the masked language modeling, we mask different or random words in the sentence to create more, more data points in our data set. Another thing I want to say is, why do we start with language modeling? We found that if a model is trained with language modeling, so is pre-trained with language modeling, so we have a big model, we train it to do language modeling, so to predict the next word, and then we just fine-tune it for question answering, for example, or semantic analysis, or any other task. It gives like really better results, because it kind of understood the language, and then we fine-tune these parameters to get to the right task that we want to do. And this is exactly what we are going to do. So we are going to start with a model that is already pre-trained on language modeling, a BERT model that is already pre-trained on language modeling, and then we are going to fine-tune it for the question answering task. Okay. Okay, I'm going to just talk a little bit here about self-supervision and how it can be applied in NLP. So we have the masked language modeling that we just talked about. So we just mask a percentage of the words in the sentence, and then we try to predict the entire sentence. We try to fill in the blanks. And then we also have another case where we do a next sentence prediction. Rather than doing a next word prediction, we can also do a next sentence, complete sentence. So in this case, we have two consecutive sentences in the text, and we randomly remove one of them. So we randomly mask one of them. And then we have a GAN-like configuration, which is generative adversarial network. So generative adversarial network are the kind of networks that are used for example, to generate new faces, to generate new data scenes in a game, for example, generate something new, completely new. And we use and then we use this GAN-like configuration to generate and replace some random word in the sentence, and then ask the model to predict which word was replaced. So we have a sentence, I have a dog, and then I will generate a new word for dog, for example, and I would say a German Shepherd. And then I would ask my model to know which word was replaced by the GAN model or not. Just let me know if you still see my screen, please. Okay, perfect. Oh. Yeah, so these are the three kind of self-supervision that is used in NLP, and self-supervision in NLP is really gives like great results and is really used every time we want to train a model. Okay, so one other thing I want to talk about is, okay, sequence to sequence models. We are talking about the general architectures of deep learning for NLP. One of the architectures that we studied is recurrent neural network. We just gave an overview of it, how it's how everything is connected. Another really important model is the sequence to sequence models, or transduction models. And these models contain two submodels, the encoder and the decoder. So let's say we have this sentence, I have a dog. So each word has its own embedding, so I can create this matrix here. And then I would give this matrix to an encoder. So this model can be a recurrent neural network inside, a transformer inside, any type of model here that deals with text. And then this encoder will encode everything and create one vector. It will like compress all the information in the sentence into one vector. And then this vector is given to a decoder. The decoder also contains some fully connected, some recurrent, some transformers, anything. And then it will output the same sentence, of course, in meaning, but in a new language. For example, for translation, it can also output in the same language, but in, for example, if I want to just paraphrase or change the sentence or use some synonyms or anything like this. So I can also use it for this purpose. Or maybe summarize the sentence just to get the summary here. I have a paragraph and I get to hear a summary of it. So this is what sequence to sequence or transduction models are. We have an encoder, a decoder. The goal of the encoder is just to compress all the information in one vector. And then the goal of the decoder is to put these information, these most important information, into the right format. So for example, translate it into another language. Okay, and then one other architecture operation that is really used and promising, and it is the cornerstone of of transformer models. It's the attention mechanism. So one of the important things. Okay, let's talk about words that have the same spelling but different meaning. So let's say I left my laptop on the left side of the desk. If I just do the embedding, as we said, these words would have similar embeddings, but then how my model would get that this word is completely different from this word, because this word means I leave, from leave, infinitive of leave, and then this one is the left, is a position. So we need to find a way to make the model know the difference between the two words. And also, one of the other things of the attention mechanism, one of the problems that the attention mechanism is trying to solve is when we have a really long sentence, and I talk about, I talk about, let's say, a name at the beginning, and then I refer to that name by he or she at the end of this sentence. I need my model to know that he or she referred to that name, which is at the beginning. And sometimes without the attention mechanism, we lose this connection between the last word and the first word of the sentence. So this is why this is what the attention mechanism is trying to solve. And how it solves this problem is in the encoder. What you notice here is that we don't have only one vector, but we have a matrix here. And the matrix will say, okay, the first word has a certain relation with the second one. The second word has a certain relation with the third one, the fourth one, and the first one, etc. So it holds all the relationships between the different words in my sentence. And this way, we can focus on important words in the sentence. We can find some references, as I said, the first word in the sentence that is related to the last word, for example, and we can understand similar words like I left my laptop on the left side of my desk. Okay, so this is the attention mechanism, and then it's a kind of, okay, if you want some details here, the attention mechanism, I just want to see where can we get the recording. It will be in the YouTube channel of Codelabs Academy. Okay, and then if you want some more more details here, basically the attention mechanism will get the encoding of each word, and then it will compute some different vectors from the same encoding, and then using a softmax it will get the probabilities of all the different relationship between this word and all the other words in the sentence. So this is like a really basic explanation of the attention mechanism without getting to the query, value, and keys. And then the transformers is the type of model that is based only on the attention mechanism. So previously we would have some recurrent neural networks that contain the attention mechanism, but here the transformers came and only uses an attention operation with some feed forward and some fully connected layers. So basically, if we see here the general structure, so on your right, we can see the general structure of the transformer model. So we have on the left the encoder, this small part here. Can you see? Let me use a laser here. Okay, so we have here on the right the encoder, and then here we have the decoder. And in the encoder, we have this attention, multi-hat attention, which is the attention mechanism, where the attention mechanism is applied. And then we have a feed forward. Add and normalize is just applied to normalize the output. And of course, we have a recurrent layer here, and then a recurrent, a skip connection here, and a skip connection here. Okay. And this encoder is applied n times, and then we get to the decoder, and the decoder will also use the output of the previous words and also the output of the encoder to get to the right, to get to the output probabilities or the right predicted words. So we still have an encoder and a decoder, and also this one was trained on translation, and also other transformer models were pre-trained for language modeling. One thing you can see also is here a positional encoding. So here we have the input embedding. So just get the embedding from another network. And then we add the positional encoding. So one information that is missing in the transformer, because we are using only an attention layer and a feed forward, we are now doing a recurrent neural network where each node gets the previous information from the other node. We are just getting one layer that gets everything and then computes all the different relationships. So one thing we are getting is one thing we are not getting is the position of each word. So we don't know that the first word, which one is the first word, which one is the second, etc. And this is why we add this positional encoding. So some values, we change the values of the embedding to also hold the position of each word in the sentence. And then to get to the probability. Of course, in the multi-hat attention, we would get this kind of attention operation. And this attention operation uses the query key value. So we would have 3 different matrices for parameter matrices that we are going to learn, which are the query, the key, and the value. We multiply each matrix by the input embedding. So we would get the query, key, and value for each word, because we have, of course, an embedding for each word. So we multiply this embedding by these 3 matrices. We would get 3 vectors. One for the query for the word, one for the key for of the word, and one for the value of the word. And then we would multiply the query and key, and then multiply everything by the value later with the softmax. And basically here, the query and key, we get the query of the word. So we have the query of I, and I multiply it by the keys of all the words in the sentence. So I multiply it by the key of I also multiply it by the key of have. I also multiply it by the key of a and a dog. And when I multiply it, it's like computing the relationship between the two. So between the query and the key of all the different words. And then this, I will apply a softmax on it to get a probability to know what is the similarity between all these different words, or the relationship between all these different words. And at the end, I will multiply it by the value to get my final vector that represents this word. So basically, this vector will hold the information of all the other words with a certain probability. So maybe 90% of the first embedding, because it will hold all the information by of itself. Of course, every word is related to itself. And then maybe 10% for dog or something like this. I'm just gonna check the chat. Will there be certificate for this section? No, I'm sorry, there weren't. This is a free workshop, but then there is certifications on the Code Labs Academy. How is the attention mechanism trained to know what to pay attention to? Yeah, so during the training, we learn this query, key, and value matrices, which are weight matrices. And by learning these matrices, we would learn what to pay attention to in each word. Okay? And the fact that we are creating a new vector for each word, and this vector will hold all the information from the vector itself, from the embedding of the word itself, but also from the embeddings of the words related to it. Is it clear, Eugene, or do you have any other Okay, so the attention mechanism is used to have like this kind of computing the relationship between all the different words, so that just we know if I has a relation with this word, have had a relation with other words, etc. What is the percentage of having this this relationship? But it's not what to pay attention to. Okay, it's just computing what is the relationships between all the different words. So I want to have an embedding or a vector that represents the word, but also the relationships between all the different words. Okay, I hope it's clear. And then one prominent model, transformer model, is GPT. So GPT was created in 2018, I believe, just after the transformer. The transformer model was in 2017. And then GPT came and just modified the model a little bit. As you can see here, it modified it by just removing completely the encoder part and just keeping a masked multi-head attention and just keeping the decoder part. And as you can see, of course, we can apply this to solve multiple tasks like classification, entailment. Entailment is the relationship between a premise and a hypothesis, similarity between two sentences, and multiple choice answers. So for example, if we have a question, we want to answer, we have multiple choice, which one is the right answer to that question. Now, BERT came also after transformers, of course, and what they did is they removed the decoder completely. They just kept an encoder and with the repeating layers, of course. And they changed the tokenization process. So they have like some tokenization is basically where we have different text with different sentences and we extract all the different words in the sentence. So what are we going to do with the punctuation, for example? Are we going to remove it? Are we going to encode it into some sort of token or encode it into some sort of word, etc. So this is the tokenization, and they use the special tokenization of BERT, and they also use this only encoder model. Okay, I'm going to stop here and check if there is any questions. Don't understand how training results in calculating V, K, and Q matrices. Do you have any references that explain how this training is done? Yes, of course. I will, I believe that JLMR extension blog is one of the best illustrated I'm gonna send this. So basically you have these three matrices for the query, key, and value. And then you have, okay, here the input is one sentence, thinking machines. You have the embedding for thinking, you also have the embedding for machines, and then you multiply x1 by wq, by wk, and by wv. So you get the query for the word thinking, the key for the word thinking, and the value for the word thinking, and the same thing for machines. And then what you're going to do is that you're going to multiply. So for the query, you're going to multiply the query multiplied by the key of thinking, but you're also going to multiply the query of thinking by the key of machines. And you're going to get two different values. And basically, these two values will hold the information of the relationship between the two words. And then what you're going to do is that you have the query and key. You have the query multiplied by the keys. You will divide it by 8 just to get some dimensionality normalization. And then you will apply a softmax. When you apply a softmax, you will get a probability. And this probability will say that thinking is 88% related to thinking and 12% related to machines. And then you would multiply these probabilities by the value of thinking. So basically you have this value vector that you created previously. You would multiply 88% multiplied by V1 plus 12% multiplied by V2 to get Z1, which will represent the thinking vector. And then you do the same thing for machines. And this way we train, of course, and of course we get this for each sentence in the data set. We get to the results and we calculate the loss function, and we using gradient descent we adjust the weight matrices for the query and key and value to get to the correct way to calculate the relationship. I don't know if it's clear like this, but you can find all the details in this blog I shared on the chat. Okay, is there any other questions on the architecture of the models? I have seen value key and query matrix multiplication explanations, but I don't understand why. Is there some intuitive explanation? So basically, the intuitions behind the query and key value matrices. So, okay, let's say you have, we completely change the context. Let's say you have a page ranker, you have a search, just like Google search or Bing or anything. Okay, you want to search for one thing. This is your query. What you write in the input is your query. And then you have a bunch of a data set where it contains all the different pages with all the different information for these pages. And you can consider these as the keys. And you want to compute the similarity between your query and these keys in the data set. So you would multiply the query by all these keys to get the similarity. But then the result will contain all the information from this similarity, from this multiplication. You would get to from this multiplication you would get the probability of having this page in the results, and then you will combine all these to create your results and the results that you're going to print to the user. So basically this is what's happening a little bit here. This, intuitively you have the query, this is what you're asking for, and then you have your different keys. This is what you are having your data set, and then you would compute the similarity between all these to get to to get to the pages that you're gonna put on the search results. Is it clear for the architectures? Okay, I think I'm gonna continue, and if you have any questions, just let me know. Okay. One of the things that we can see from the deep learning architectures over time is this idea of bigger the better, which is clearly true. So one of the things that we have now is GPT-3, which is 3 billion in the number of parameters. We have Megatron, which is 8 billion in the number of parameters, etc. We have really big models, and the numbers are really going bigger and bigger. Now Microsoft has also a model which is 17 billion, which is really huge and can be deployed on any smartphone, of course, and only on the server, and a cluster of different a cluster of different GPUs and TPUs and everything. So it's really, but in terms of precision, training a large model for few epochs and then compress it is the new best practice. So before we were training a smaller model and then for a really large number of epochs, and then we would fine tune it and then compress it a lot. So, but now we are trying to train a really large. When I say large now, it's 8 billion, 17 billion. The numbers are really going up for a few epochs only. And then we try to compress it to make it smaller, to shrink it by quantizing it or doing some compression techniques or optimization techniques to reduce the size of this model, and while keeping, of course, the precision of that model. I'm gonna just go back to the questions. Okay, there are no further questions. Okay, let's go to the part 3 and explain what's question answering with just 2 slides, and then we go ahead and create our use BERT embeddings and create our question answering model. Yeah, so question answering, you would get a question like this and a context. So you would get, okay, the question, for example, is the atomic number of the periodic table for oxygen, and then you would get a context. The context is a paragraph that should contain the answer to the question. And then you have here in the context, oxygen is a chemical element with symbol O and atomic number 8. It is a member of the collagen group, etc. So basically what we want our model to detect this, atomic number 8. We want our result to be, our answer to be found in the text. And you can find this in the Stanford question answering dataset. So Squad 1.0 or 2.0 are really used in the literature. So you can, it's a free dataset, so you can download it and explore it via this link. And you have different types of question answering. So you have the extractive question answering that we are going to code in this workshop. So basically you extract the answer from the input, and the input is the context. And the input can be like a web page, it can be anything, really anything. And the goal is it reads this paragraph and it knows that it is looking for the atomic number, so it goes to this and print 8. And then you have open generative question answering. So here the model generates new text from the context. So it is true that you have this context, it detects that you have atomic number 8, but it doesn't only give you, okay, atomic number 8, or it doesn't only highlights this. It will give you a full sentence like the atomic number of oxygen in the periodic table is 8. This is like a generate a new text from the context. And then you have closed generative question answering. And in this case, you have no context that is provided. So you don't provide this, you just provide a completely, the question answering model will completely generate an answer by the model. So if you say, okay, maybe this is a case in chatbots, for example, where you ask it, are you funny, or are you a robot, or something like this, and then the chatbot will completely generate its own answer by its own. Okay. I'm gonna just check if there is any other questions. Okay, perfect. And then we have, okay, what we are gonna do is that we're gonna use this BERT model, but we are also gonna adapt it to question answering. And BERT, in their original paper, they suggested to adapt it in different ways. So to do some question answering, to do some entailment, to do some text classification, etc. But basically what you have your two questions. You have the question and the context, which is a paragraph, as input, of course, of the model. And then you would have the outputs here at the end of your output vector. So at the end of your output vector, you would get the final sentence, because these other outputs corresponds to other tasks. So for example, C here correspond to the class in the text classification, and then T1 to Tn correspond to another sentence if I want to do something like, okay, I want to predict 2 sentences or something like this. So this corresponds to another task. And then the last sentence in our result will correspond to the answer in question answering. And this is why we can use BERT really easily, because it was already trained for language modeling, and we are just going to fine tune it for question answering for this task. All right, so I think we can go ahead and go to the code. But if you have any other question before I go, just let me know. Okay, what about the question answering system that depends on textbooks? What kind of domain are these systems, open or closed? It depends on the answer, actually. If we want the answer to be completely generated, you mean from textbooks? Okay, so it's an open question answering. So it means that, okay, we have some textbooks, we want to find the answers in these textbooks somewhere, but we don't want to generate a new answer from scratch. Like I may ask, so in the closed question answering, I may ask the model, okay, what is the atomic number of oxygen? And it may answer 13, 30, etc. because I said number, so it detects that I need a number, but it doesn't know, because it doesn't have these textbooks, so it doesn't know that the atomic number is 8. So if you have textbooks and you want to find the answer in somewhere in these textbooks, then it's open question answering. Okay? Okay. Any other question before we go to the final code? And we would, okay. So while if you have any question, please ask. Otherwise, I'm going to start by explaining what I'm going to use in the code. So basically, I'm going to use first, are you seeing the Colab, the notebook, correctly or not? Just let me know if I need to zoom in or do something else. I'm going to check the chats. Okay, maybe I can zoom in a little bit. Okay. Okay, I think like this, it's fine. Okay, so what I'm gonna use is I'm gonna use 2 special packages. So the overall model uses PyTorch, which is a deep learning framework, but I'm going to use two different packages that are helping to create the models, etc. So we are not going to code BERT from scratch. We are not going to train it. We are just going to fine tune it, train it for 3 more epochs on the question answering tasks. So we have the package transformers. So transformers is a package that holds all the different transformer model for NLP, and also all the different pre-trained weights, data points, so that you can take the file and call it in a pre-trained way, etc. And you also have this dataset package, and dataset really easily load Squad version 2, so we can directly use it, and it's really easy to use it to load the dataset, create the labels, etc. And then we have some other packages that we are going to use just to display the data set, display some images, etc. Okay, just before we start, we are going to use Squad. We are not going to use version 2. We are going to use version 1. We could use version 2 easily just by changing this Boolean to true. And then it's just a matter of size of the data set and training size, because the training would take a lot longer. And then model checkpoint, we would use the BERT base encased. This is just the name of the checkpoint of BERT in transformers. And then we just set the bash size to 16. Of course, we'll load our dataset using this function, which is directly from the datasets package. Okay, and just here, if we put this to true, then it will load Squad version 2, else it will load Squad version 1. Okay, and then we can check our data set. So the data set would contain some features. We have the training part and the validation part. And in the training part, we have different features per data point. So we would have the ID, we would have the title of the question. We'll also have the context. As I said, the context is the paragraph where we are looking for the answer. We'd have the question and, of course, the answer. There may be different answers per question, so a number of answers is normal. Okay, I'm going to check if there is any question. Okay. And in the validation, we would have the same thing, of course, but the number of rows is pretty different. So we would we have 87,000, around 87,000 question answers for the training set and 10,000 for the validation set. We can take an example here. Okay, let's check the answer. The question: to whom did the Virgin Mary allegedly appear in 1858 in Lourdes, France? And then you can have like the answer. Where is the answer? Okay, the answer start here. Saint Bernadette Soubirous. Okay, and you can find, of course, this answer in the text, but we just wanna, we just wanna extract it from the text and put it here, so it's in here. Okay. And then, here I'm just gonna print random elements from the dataset. I think I'm gonna start the session again, but it's fine. Okay. Basically, we're gonna just print them in a fancy way using pandas just to get all the random data points from this dataset, but it's fine. Okay. Oh, I know why it's taken long, because I started the training before we start the workshop, just to get the training ready, because it takes a lot of time. Of course, I believe it didn't finish yet, but hopefully it will finish when we arrive here. Okay. So basically this this cell won't run until the training finishes. Okay, it's fine. Okay, no question. Okay, and then auto tokenizer. So auto tokenizer uses the BERT tokenizer to tokenize everything. As I said, tokenizer means dividing the sentence into words and then getting the inputs, getting the IDs or the indexes of each word from the vocabulary or from the dictionary. So we get the pre-trained tokenizer, because BERT has a special tokenizer. So we get the pre-trained tokenizer. We use it, for example, in this sentence to I have a dog, and we get the output of this I have a dog in this form. So we get the index of I have, etc. And each sentence is padded so that you have different kind of length for each sentence. So here, normally you would have like different yeah, you would have different paddings for the start of the sentence, the end of the sentence, etc. Yeah, just another, basically you have just another index here to represent the start of the sentence, and another index here that represents the end of the sentence. And in between you have the 4 words, I have a dog. Okay, and then you just give the maximum length of a feature. So what is the dimension of each embedding, and also what's the doc stride? Basically, the doc stride is what are the distances between two different, what's the collab link? I'm going to share the code at the end of the workshop. I'm going to ask them to send it to you all by email. Okay. And then here we just like compute the length of different results of the tokenizer on different questions and different contexts, just to check if we are doing something special. Okay, and then here we apply everything to all the questions and answers in our data set, basically. Okay, so this is for the tokenization. I don't want to go a lot into the details because we are almost running out of time. So we need to go to the model and how do we use the model. Okay. Just checking if there is any other question. Okay, and then basically what we are going to do is to call this auto model for question answering. And then we would give it the pre-trained. Of course, this pre-trained is from the BERT model, and this BERT model was trained to do language modeling. And we are just gonna train it, fine-tune it a little bit more for the question answering tasks. And what we are gonna give it some arguments because we need some training arguments. So we want to give it, okay, what's the train evaluation strategy? When do we stop? We stop at a certain number of epoch. What's the learning rate? What's the batch size, the training batch size, or the evaluation batch size per device? So if we have like different devices in our cluster, we can use like, okay, different batch sizes for the device. So if I have like 2 GPUs and I have 16 in the batch size, I could use 8 and 8. Each one of the GPUs can use 8. If they have different performances, then I would maybe use like 12 and 4, depending on the performance of the GPUs that I have. And then the number of training epochs, I'm not going to put a lot, it's just 3, just to fine tune the model on the question answering task. It's already, we already trained the model for the model language modeling. So the model is already trained. We just want to put the right weights or modify a little bit the weights in order to conform to the question answering tasks. And then the weights decay, and push to hub is just for the Hugging Face or the transforming package. They allow us to push to the hub and get all the results in their Hugging Face website. So I guess I'm gonna write here. I'm gonna write here the website so that you can go inside and just check it. So if you have like a website, an account here, you can check the results on the hub after the model is trained, which is pretty cool. Yeah. And then, yeah, this is what we have here. And then, of course, we have a data collator. This is also like from where do we get this data, and just given what are we going to do with the data, etc. And then we have the trainer. So the trainer, we give it the model, the argument for the training data set, the evaluation data set, and the tokenizer. And this will, and then and then just doing trainer.train will run everything, and will launch the training, and everything will run hopefully smoothly. So basically we would get all the results here. The training is almost done, but it's already 1 hour. 1 hour of training already for 3 epochs. As you can see, it's really time consuming. Don't forget to put here in the runtime, you change the runtime to GPU as to use the GPU like training, otherwise it would take like days in the CPU. So don't forget to change it. And yeah, it takes a lot of time just to fine tune the model. So just imagine how it takes if we were to train it from scratch. Oh, docstride is what we are using to, okay, so docstride is given to the tokenizer just to know what's the length between two sentences. So for example, if I have like multiple spaces or multiple entries and go beyond that space, so I'm just gonna say, okay, you find the first sentence and then you go back and you take a lot of you take that number of sentences within the same one, etc. So it just it's just a hyperparameter that is given to the tokenizer to say what is the stride between two different sentences in the dataset. So if I have a context, what is the stride between these two different sentences? All right, it seems that this model is not gonna finish on time, but maybe we can stop it. Let's hope. Okay, let's just stop it and see. It did finish 1 epoch, so at least we have that. And it is running the evaluation. So let me just save my model like this. Of course, the results won't be good, but okay, we're gonna, I think we're gonna do without it. So basically here I'm saving the model weights into, you just give like a name for the weights of the, for the file weights, QA workshop. As I see, even saving the model takes a lot of time because it needs to go in the model and save all the different weights for all the different layers, and BERT is pretty large. Okay, so basically once the model is saved, what you can do, it's upload the PyTorch model. Okay, it also sends everything to the hub so that you can check the hub again. As I said, you just log into the website. It's on the top of this notebook. I'm going to send you this notebook at the end. So you just log in here and then you get all the information. Is your model trained or not? How does it perform, etc. So it's really cool to have this, all the logs somewhere, but it takes time, of course. Okay, and then what we are going to do is that we're going to take this model and just test it on new data sets. So basically, we're going to take the evaluation data set, get eval data loader, and then we are going to just get the output for all the different values in our evaluation data loader. And of course, we're going to check the shape, if they are in the right format, if we have the same number of rows with the evaluation validation data set. We're also going to go over all the results, over all the outputs, and just print them in a correct way, like the score and the text of the answer, like how it is what's the answer basically. Because of course, don't forget, here the answers are still tokenized, so we have numbers, so we need to go back to the vocabulary and convert the answers as well, because the answers are just a bunch of numbers. So we need to go back to the vocabulary and get the answer in a text format and put it here. And basically this function is what we do. We go into this valid answer valid answer array, and the array will contain different different dictionaries, so we fill in the blanks in that array. Yeah, and then the row prediction on the validation set, we do the same thing, and we can compute, of course, the we can post process the QA by computing, for example, the score and everything, and saying, okay, our model performed this and this accuracy on the question answering on squad version 2 or 1 as you want. Okay, one thing I wanted to point out, I don't know if it's saved or not yet. Okay, not yet. One thing I wanted to point out is that we can also have like a no answer probability. We can add that just to say, okay, I want to, if the model is not confident at 90%, I want to answer the model to say, okay, I don't know the answer to that question or something like this. So that's pretty cool, and it makes the model know that, okay, sometimes you can get it wrong, or you may not know the answer. And we have this kind of confidence score, so we can know if our model is confident enough of the answer or not. So that's pretty cool. Okay, so I think even the saving will take too much time. It's still on 48%. So we're gonna stop here, and I'm gonna send you the notebook as well as the slides, and you can go through the notebook, and if you have any questions, please ask. I'm gonna send here my email again. Okay, I'm gonna put here my email again.
Can you also share the
Yep.
Can you also share the recording of the session?
Oh, the recording will be available in the YouTube channel.
Okay, what is the YouTube channel name?
Yeah, so just look for Code Labs Academy.
Okay. Thank you, Heather.
Okay, no problem. No problem. All right. Have a nice day. How is fine-tuning captured in the model? Does it change the VQ matrix value? Exactly. So when training the first time, we change the value key and query matrices in the attention mechanism. So we change all the weights of the model. The model contains the attention and also the fully connected. So we change all the weight matrices, and the value key and query matrices are weight matrices. So we change all these in the training. We adjust them to the correct values for the language modeling. For the model, the language modeling. And then we want to fine tune it for the question answering. So we start with the adjusted values, and we train again. So we adjust for a small number of epochs. Here we put 3. So for this small number of epochs, we adjust for a little bit more in order to fine tune these numbers or these values for the question answering task. There is no neural network weights being adjusted also? Yeah, of course. So, yeah, of course. So after, let me just share this screen. Maybe, maybe I missed it in the explanation. So here in the encoder, we have an attention mechanism that is in orange, and we also have a feed forward. So we also have a fully connected neural network after the attention. So we apply the attention and then a fully connected, attention fully connected. And these are the weights that are adjusted during training. Is it clear, Eugene? Still wondering how training works. So training works as with all other different networks. So if you see in a standard neural networks, in a fully connected, what you do is that you do a feed forward, you do a complete feed forward. So you get to the results, you compute the error, you calculate the gradient of each error for each value of the weights, and then you adjust that value using gradient descent, for example. And it's the same thing that is happening here. It's not different from it. So each of the weight matrices, we calculate the and nothing is discretized during the training. So everything is still continuous. So we still can compute the gradients. This is why I don't do you know how the training works for a fully connected, and you don't understand it for this special case? So why is the attention mechanism a problem? Like if there was like some discretization or anything else, then I would understand that the gradients won't be computed anymore. We could not compute the gradients anymore, so we cannot adjust the weight. But it's not the case. So here it's still continuous. Yeah, just imagine it as having 3 different linear layers with 3 different matrices, and we call these matrices the value, the key, and the query. So just imagine it as having 3 different fully connected linear layers. And these linear layers can be, their weights can be adjusted because everything, the gradients can be computed. Okay, so please don't hesitate to ask if you have any questions, even via email. If you have a code and you want to understand something on it, just ask. All right, so I think I'm gonna terminate the call now. Thank you everyone for being here. If you need anything, of course, please ask. This is one of the free workshops of the Code Labs Academy, but we also have a certification where you can learn more about data science and deep learning. All right, so have a nice day. Thank you.